Okay, so today what we're working with is chemical bonding, like for example, combining sodium and chlorine to create sodium chloride, which is table salt, and building water and so forth. So that's where we are. And in order to create a bond, really the way that works is you work with the outer shell of each atom. Now you have those energy shells that we talked about. So the first energy shell is a low energy shell, and then you have the second and third and possibly more. We're not going to deal with really huge atoms. We'll deal with relatively small atoms, so we won't get up into the big, huge outer 5, 6, 7 energy shells. But anyway, the very last shell is the one where chemical reactions take place. The very last shell. They call it a valence shell. Now that will be in the PowerPoint, so you don't need to write that down, but it is called valence shell. So the electrons within the valence shell of the atoms that you're trying to bond together, or that do get bonded because, you know, it just happens in nature, and that's where the reactions take place, just in that valence shell, that outer shell. So that's very, very important that we understand how to assemble an atom. So in this particular case, what we're working with is an atom that has, let's see, these represent the electrons. Here's the nucleus. So what we're looking at is an atom that has 2 electrons in the first shell, and then 1, 2, 3, 4 electrons in the second shell. Well, we need to know how many electrons each shell can hold. Okay, so let's look at that. Let's just start with, let's say, first shell, and we're going to put shell here. All right. I should actually write that right here. Energy shell. We'll put that. All right, so first energy shell, that one can hold 1 or 2 electrons, and that's all. We cannot hold more than that. So 2 would be maximum. So we'll put number of electrons. Okay, it can hold 1, or it can hold 2. 2 would be maximum, which you can see in this particular diagram. They're only putting 2 electrons in the first energy shell, the one closest to the nucleus. And again, that is the lowest energy shell that there is. And 2 would be maximum. That is filled. Now, the filling state is very important. Oh, by the way, this was left in lab, if anybody, yeah, okay. Anyway, so I've been carrying it with me all over town, you know, clutching it. Not really. Okay, so that's the first energy shell. And then we go up to the second energy shell. Now, you always begin filling the first energy shell first. So if you have 1 electron, that you just put 1 in the first shell. If you have 2, you put both of those in the first shell. If you have 3 electrons, 2 of those would go in the first shell, and then 1 would go in the second shell. So begin filling shells from the inside out. So we filled 2, and then we had 1 left over. If we had 3, that obviously would have to go into the second shell. The second shell can hold anywhere from 1 to 8 electrons. 8 is a filled energy shell. And the point in having a filled shell is if we can get atoms to have filled shells, they become stable. They're not reactive. So some atoms just in nature are not reactive, which means they will never bond with any other atom. If on a periodic chart, if you look at the column, the vertical column, which would be a group, but it's not labeled 1A or 2A or 3B or whatever. It's called the noble gases. Sometimes it's referred to as the inert gases. Okay, that's to the far right, the noble gases. All of those have filled outer shells. All of those already have filled outer shells, which means they will never react with any other atom. So if you have a helium balloon, obviously you fill it with helium, those atoms will never bond with anything. So if you take the balloon and you breathe in the helium so you can talk like Donald Duck, those are actually expanding the vocal cords, but they're not bonding to your vocal cords. They're not bonding to anything. So when you exhale, you're losing that helium. So it doesn't hurt anything to actually breathe that in. So don't worry about that. You can take in helium. Some people worry about that, like, oh no, it's going to attach to my brain and I'm going to end up like Soft G, you know. But actually it doesn't. In fact, all of those noble gases have filled outer shells. Their last shell will be filled. So neon, same thing. It doesn't bond with anything. They always exist as individual atoms. Argon, krypton, it does exist. Xenon, radon, you've probably heard of that. But anyway, all of those are noble gases. They exist as individual atoms. But those are the only atoms on the planet that already have filled outer shells. So other than that, everything else on this chart is reactive, which means by itself it's going to react with something. So I couldn't take a hydrogen atom and just release it into the atmosphere and it not attach to something. It would bond with something. I cannot take any other atom on this chart and release it without it forming a bond with something else. So those naturally form bonds, all the other atoms. Okay, and so you have to have filled outer shells or valence shells in order to be stable. So third shell, now this one is a little odd, at least with the information I'm going to give you. It can hold anywhere from 1 to 8 electrons. 8 is filled, and it can also hold 18 electrons. That can also be filled. So it has two filling states. Now, in order to explain that, it would take probably 2 days in order to explain why that is the way that is. I don't have the time. And it's not necessary that we know that information. You will get that information in the chemistry class. So we're going to let the chemistry instructors handle that for you. That's not a biological issue. That's not what we're working on. So there are 2 filling states for the third energy shell. Fourth energy shell, there are actually 3 stable states there. It can hold 1 to 8. It can hold 18. It can hold 32. But the 8, the 18, and the 32 are all filled energy shells. But you would have to have a tremendous number of electrons in order to fill up the fourth energy shell with 32 electrons. So you'd have to fill the first with 2, the second with 8, let's say the third with 8, and the fourth with 32. So if you add all that up, you have a large number of electrons. And you don't, there are some atoms that do have that many, but we're not going to be too concerned with that. Okay, so that would be, and I'm not going to go into the 5th, the 6th, and the 7th energy shell. All right, so you can see this is the second energy shell that we have. You have 2 electrons again, these blue spheres, so we got 2 in the first shell and we have 4 in the second shell. So if we're looking at the second shell, it is only filled, which means it will only be stable if it has 8 electrons. This one only has 4, which means it's reactive. Okay, so the element that has, now keep in mind, and we said this before, the number of protons will equal the number of electrons on the chart. That doesn't mean it's going to always be that in nature. You can remove electrons, you can gain electrons, you can share electrons, but on the chart itself, the number of electrons is always equal to the number of protons. So if you look at your periodic table, I like to say periodic table, periodic chart, I don't know, for some reason. No, I like to say table. Periodic table, anyway. If you're looking at group 4A, so that's the vertical column again. Group 4A, the very first element you have there is carbon. Notice in the upper right-hand corner, you see these two really small numbers. You have a 2, and then you have a 4. That's what is referred to as the electron configuration. The 2 is the number of electrons in the first energy shell. The 4 represents the number of electrons in the second energy shell. So they actually, on a periodic table, they tell you exactly how many electrons you have in each shell. It's just written right there for you. Okay, so my second energy shell, which is a valence shell, the last shell, only has 4 electrons. It's not filled. So we know it's going to be, we know it's not going to be stable, it's going to be reactive. So in order to fill the second shell, and if you look up here, again, we need 8 electrons to fill it. So in order to have that filled, I need 4 more electrons. I'm going to get those from other atoms. So for example, we can, and I'm going to remove this because it's in my way. Maybe I'm not. Turned it off somehow. There. It had to think about it. This is in my way for the moment. And this will be 2. That out of the way for the moment. All right, now, back to black. All right, so what I want to do, so this is carbon. Now I've got 2 in the first shell, 4 in the second shell, so I have 6 electrons. The atom or the element that has 6 protons, that's going to be carbon. Carbon, the atomic number in the upper left-hand corner, if you look at the element carbon, it will have a big 6. That's the atomic number, tells you the number of protons. So I know I have 6 protons. I can place those in here. And the total weight of this, rounded to the nearest whole number, is 12 atomic mass units. It actually says 12.011, so we round that to the nearest whole number. 6 protons will have a mass of 6 atomic mass units. 6 electrons, the mass is negligible, very tiny. Okay, so we need the number of neutrons. 6 plus what is going to give me 12. Obviously, I must have 6 neutrons. That gives me the mass, the total mass. So your mass is really the number of protons and neutrons. Each one will weigh 1 atomic mass unit. So if you add those together, you're looking at a total of 12, 6 protons, 6 neutrons. That will give you the 12 atomic mass units. Okay, so I have then, I've determined the number of protons, neutrons, the electrons are already given to me, so that was pretty cool. Now what I want to do is I want to fill the outer shell, the valence shell, which is, in this case, the second shell, which only has 4 electrons, and it needs to have 4 more, which would be 8, which would be stable. Okay, so what I can do is, if you look at hydrogen, hydrogen has 1 proton. So in the nucleus, I can put 1 proton. It doesn't have any neutrons, at least not this particular isotope of hydrogen, because the mass is 1 atomic mass unit, rounded to the nearest whole number. It says 1 is the mass. So the proton we know weighs 1 atomic mass unit. 1 plus what would give me 1? Well, 1 plus 0. I don't have any neutrons. So you could just put 1 proton and leave it, or you can put 1 proton and 0 neutrons. And then I have 1 electron. So I'm going to place 1 electron here. Now I'm sharing those 2 electrons. So this is a share experience. I'm not transferring, I'm not gaining, I'm sharing. So I now have 2 shared here. I'm going to do the same thing with this one. I'm going to share a proton here. An electron. So I have the 1 proton in the nucleus. That doesn't look like a P. Here it does. Okay, we'll put another one here. 1 proton. And we'll put a fourth hydrogen here for sharing, and that is one proton. So hydrogen is the simplest element on planet Earth. The simplest. They don't get any more. They don't get more simpler than hydrogen. It only has one positive proton and one negative electron. The simplest. Now, the most fascinating thing to me about hydrogen is anything that's living, whether it's you, whether it's a plant, whether it's a bacterium, whether it's a fungus, it doesn't matter. Everything on life uses hydrogen as an energy source. That's what we run on. That's what we run on. This is our energy. So when we take food and we consume it, what we get out of that in order to be able to walk across the room or talk or drive the car or do whatever, make up the bed, whatever it is we're going to do, shower in the morning, shave, it all takes energy. We use hydrogen to do that. So to me, it's very interesting that, and this is just my opinion, that God created a world where anything that's living runs off of the simplest element. What a beautiful system. It is amazing. It's quite amazing, and we'll talk more about that. But anyway, I love that idea. The simplest element actually runs everything on the planet that is alive. And so we drill and we take out gasoline. We run our automobiles, and your waste product on that is carbon dioxide and so forth, which affects the planet, creates all kinds of problems. When God has already said, the most energy efficient system we have, which would be the living system, runs on hydrogen. So why don't we design things to run on hydrogen? They're just now starting to do it. There are some automobiles that run on hydrogen. You only have hydrogen pumps in California. So you can buy hydrogen-powered automobiles, but they're only going to work in California. So you're not going to get very far in Texas. So at some point, I really feel in your lifetime or your children's lifetime, everything will run on hydrogen. And to me, and I'm a little bit off topic here, but the most wonderful thing about that, your waste product that will come out of that, out of the tailpipe of your automobile, is going to be water. Doesn't hurt anything. Your waste is water coming out of that. Beautiful. Absolutely beautiful. So hydrogen future, mark my words, if you got an extra $1,000 to throw into something, into the stock market, put it on hydrogen power. Find a company, hydrogen power, put $1,000 on that. By the time you're my age, this is like investing in Walmart before there was even ever a Walmart, ever. And you will be mega wealthy. I'm just telling you. I would stake my life on this fact. I'm very confident in this, very confident. So anyway, use that information any way you want to. Okay, so back to this, what we have on the PowerPoint here. I have filled the outer shell of my valence of this carbon atom. So I now have 2, 4, 6, 8 electrons in the last shell, which is a valence shell. It's filled. This is stable. So this is a C4H, it's a C1H4. Normally they just call this CH4. CH4. This is methane gas. Methane gas. Very common. This is what we refer to as flatulence. If you prefer, we can use a more vernacular term, more common term, which we call a fart. You have what they call the Bohr diagram of a fart right here on the board. If you want to impress your friends, you can say, I can draw a fart, and you can do this for them. I don't know if they will be impressed with that. sure my friends would not be impressed with that. I have never done that, or I have yet to do that. Maybe someday I can pull that out. Things get a little slow, conversation goes into a lull. You can go, hey, brothers, let me show you this. I haven't done that yet. We'll see. Okay, so 1 carbon, 4 hydrogens. It's stable, methane gas. Its outer shell's filled. But I had to do that sharing electrons. Now you look at that and you go, well, there's another way you could have done that. You could have taken just every one of these blue spheres in this last valence shell, and you could have pulled it off and put it on another atom. That's a possibility, to take each one and pull it off. But in the case of carbon, it typically shares electrons. It doesn't lose them. So if you did lose all 4 of those in the valence shell, then you would only have 2 in the first shell, and that would be filled if you lost all 4 of the blue ones in the last shell. But carbon typically forms covalent bonds, which are called covalent bonds, which is where you share. So that's how that will work. Okay, any questions on this? Then it's going away. All right. So once again, I don't typically ask, are there questions, because I expect you are adults. And if you have a question, you just ask it. All right, so they're showing you the Bohr diagram. That's B-O-H-R. Is how you would spell that, the capital B, because it's named after the gentleman who wrote that. And so we give him a little bit of credit. Bohr diagram, so they're showing you the Bohr diagrams of all of these atoms, and if you want to refer to that, obviously you have the PowerPoint to look at on that one. Okay, so really, seriously, if you want to do this, take your periodic table, and for each one of those, say like for hydrogen, you have 1 proton and 1 electron. Well, they didn't put the 1 proton in here. I prefer in here. They didn't do it, but they did put the 1 electron here. For lithium, you've got 3 protons. There should be 4 neutrons in here in the nucleus, because the weight, atomic mass of lithium, if rounded to the nearest whole number, would be 7. So 3 plus what would give me 7? Obviously, I have 4 neutrons. Now, the number of protons, which is 3, is equal to the number of electrons. 2 in the first shell, 1 in the shell. But your periodic table tells you that. You have in the upper right-hand corner of that box, it says a 2 and a 1. That's your electron configuration. It tells you exactly how many electrons you have in the first shell, the second shell, the third shell, no matter what. It's already in there. So this one only has 1 electron in that second shell if we're looking at lithium. Okay, well, if I want to fill that second shell, that means I have to put 7 more electrons in that second shell. There's another way you can accomplish that. You could lose that 1 electron in that second shell. Do you think it's easier to lose 1 or gain 7? Lose 1. Just makes sense. Okay, so that one tends to lose that 1 electron. In fact, if you look at all of the elements in group 1A, beginning with lithium, hydrogen's a little different. Every one of those have 1 electron in their valence shell, their last shell. So they tend to lose 1 electron. That's what they typically do, lose 1 electron. Okay. Now, if you look at group 7A, that begins with fluorine. Every one of those in the valence shell, the last shell, have 7 electrons. That's why they're put in group 7A. They have 7 electrons. In order to be filled, they just need 1 more electron. So it's very easy for any element in group 1A to lose its electron to any element in group 7A. Those in group 1A need to lose 1 to have a filled outer shell. Again, look at lithium. You have a 2 and a 1. It needs to lose that 1, or it could gain 7, which is not going to be reasonable. It would lose the 1, and it could pass that 1 electron to any element in group 7A. It could pass it to fluorine, which would give fluorine 8 electrons in the second shell. That would be filled. It could pass it to chlorine. That would fill up that valence shell. It could pass it to bromine or iodine or acetone. So same thing with sodium. In group 1A, it has 1 electron in the valence shell. It could pass that 1 electron to any element in group 7A. So you could have sodium fluoride, sodium chloride, sodium bromide, and so forth. And that's a transfer. When we do a transfer, we're going to call that an ionic bond when you do transfers. So we'll get to those. You don't need to write it. It'll be in here somewhere. I'm just speaking away from the PowerPoint. I'm not following my slides. All right. I'll try to stay on my slides. Valence shell, that's the very last energy shell. We've discussed that. Chemical bonds, that's an attraction of 2 or more atoms. It's really a magnetic attraction when it gets right down to it. I can show you that. Okay. Now, we just looked at the covalent bond with methane, CH4. We shared the electrons, 4 hydrogens with 1 carbon. And we shared the electrons. We shared at 4 places. And that gave the carbon the 8 electrons that it needed to be filled, and it would then at that point be stable. That outer shell it must be filled or it is not stable. In fact, if you don't have it filled, I can promise you it will still be stable. Okay. Now, if you have, and we stated this before, if you have 2 or more atoms that are of different elements, like hydrogen and oxygen, that bond together, it's called a compound. If it's 2 different elements that bond together, they call it a compound. But anytime you're sharing electrons, that's referred to as a molecule. So CH4 methane is a molecule because we shared electrons. And it is also true that water, you're going to share the electron with hydrogen and with oxygen. So that's going to be a covalent situation as well. So water is also called a molecule. It is a compound and it is a molecule. You have 2 different elements, hydrogen and oxygen, that makes it a compound, but they are bonded by sharing, which makes it also a molecule. So that can be a little confusing. Yeah, well, if it's 2 different elements, it's a compound. Right. Like sodium chloride, that's a compound. But sodium chloride is not covalently bonded, and we'll show you that. That's where you lose an electron, you gain an electron. But so if it's 2 different elements that are not covalently bonded, you're looking at a compound. And then if they are covalently bonded, even if there are 2 different elements, you would refer to it as a molecule. So you can have 2 different elements, which make it a compound, but then if you have the sharing of the electrons, that makes it a molecule. So I know that's a bit confusing, but you know, it's just terminology. You just kind of have to get that straight in your head. And it's just one of those things. It's a hurdle, what I call a hurdle. You have to get over this hurdle, and then there'll be another hurdle you got to get over, and eventually, you reach the finish line. It's called, you finish the course. And there's another finish line. It's called you have your diploma. And there's another finish line. Maybe you get another diploma. There's another finish line. You get to buy a refrigerator with an ice maker on it. I love those because if I want to make a bourbon and water, I just stick that glass in there and it goes clink, 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 clink. Slosh a little bourbon in there, a little water at the fridge. It'll push out some water. I just swirl that around and I'm ready to go. Life is moving on. It's a weekend experience for me, not a weekday experience. Anyway, so here you have, now notice all of these are covalent bonded. that we're looking at now. Hydrogen gas, each hydrogen has one electron, and it's sharing that with the other hydrogen's electron. So one hydrogen has one, the other hydrogen has another, and they're sharing those. That gives both hydrogens 2 electrons. So it's stable. You're sharing electrons. It's covalent. So it's also referred to as a molecule because you share the electrons. It is covalent. You're sharing. That makes it a molecule. This is what they call the Bohr diagram when you're using the circles and putting in the electrons. The structural diagram, if you look at that, you write the element symbol, you use a line. That line represents these 2 electrons that are being shared. And then, of course, you write the other hydrogen symbol. So it's H-H. It's much easier to draw a structural diagram than it is a Bohr diagram. And we get away from Bohr diagrams very quickly because we don't want to be drawing all those circles. But we need to know how to do those. And, of course, I'm not clever enough to draw a space-filling model, but that's what that would look like. Okay, so oxygen. Oxygen, we have 2 electrons in the first shell, and we have 6 in the second shell. But if we have 6 in the second shell, if I share 2 electrons from one oxygen and 2 from a second oxygen, then those 4 are being shared between the two oxygens. So then if you're looking at the first oxygen, let's look at the outer shell. You have 2 electrons, 4 electrons, and then you have those 4 that are shared. That gives you 8. And if you look at the other oxygen, you have 2 and 2 more, and then the 4 that are all being shared. That gives you 8. So both atoms have filled shells. And if you had only shared 2 electrons, they would not have filled shells. So you had to share a total of 4 in order to fill up that valence shell. So we have a double bond, double covalent bond right there. Oxygen gas, the one that we breathe, that's what we breathe. It's a double covalent bonded molecule. It is a molecule, covalently bonded. Methane, we've already drawn that. And of course, we didn't draw the structural diagram, but that'd be easy enough. Carbon with a line to hydrogen, carbon with a line to hydrogen, carbon with a line to hydrogen, carbon with a line to hydrogen. You get your structural diagram, much easier to diagram. Here's water. And again, we have to fill up the valence shell. So oxygen has 6 electrons in the valence shell. So then I have, you can count 2, 4, and then 1 that is being shared with each hydrogen's electron. So 2, 4, 6, and 8, because we are sharing the electron from hydrogen with the electron from oxygen. So then hydrogen has 2 electrons in its only shell, which is filled, and oxygen has 2, 4, 6, 8, because we're sharing those electrons. So it is filled also. So that's stable. Water, of course, is very stable. And this would be your structural diagram on that. Notice you get a bond angle. That changes. I love water. Water is way cool. I have a friend of mine that actually was a very bright lady. Well, I'll call her an acquaintance because the more I got to know her, the less I liked her. But so she was an acquaintance. It's very seldom I dislike people, actually. I probably count the people I dislike on one hand. But I'm not sure I disliked her. I just didn't like her. That's not a dislike. It's just someone I really am not fond of. Anyway, all right. It doesn't matter. But you have this bond angle here, and it gives water many, many different properties, which are very cool. And it acts very differently than any other compound on the planet. It's very unique. But this woman, a very intelligent lady, she was looking for a course to take, a science course, and she's not science-minded. And so she was going to Rice University, and she was going through the catalog trying to find a science course, and she found a course called water. She thought, surely I can pass that course, lab science, water. And she did. She made a B, but she's very bright, and for her to make a B in a course, I thought, Man, that must have been a tough course. I couldn't imagine that she would ever make that grade, but she did. And so the point being, you can make an entire course out of just water. There is that much information about it. We'll talk a lot about it. It's pretty fun. It's a very fun thing. Okay, one thing that you'll notice with water other than that bond angle, well, let's talk about that bond angle just a second. That bond angle changes depending on the temperature. Let's say, for example, we have people all in an elevator, and let's say we're all oxygen, and let's say our arms are the lines that lead to the hydrogens. Okay, so if we're standing with that bond angle that we have right here, so we're all standing in that elevator, and our bond angle is that one, we can only squeeze so many people in that elevator. Well, what happens is if the temperature in that elevator were to get cooler, that bond angle would decrease. Those hydrogens would get closer together, so your bond angle would decrease. So what would happen then is you could put more people in that elevator. Well, those are really water molecules, not people. So the bond angle would decrease. So you could squeeze more people in, which means you could put more water in the same elevator, same unit of space. So bond angle decreases. Okay, until you get to 4 degrees Celsius. Now at 4 degrees Celsius, your bond angle is as small as it can possibly get. It's as tight as it can possibly get. So at 4 degrees Celsius, when water gets to that, the bond angle is really, really close. Whatever it is, it's a very tight angle. Now, below 4 degrees, you go to 3 degrees Celsius, the bond angle starts to go back up. And 2 degrees Celsius, it goes back up. 3 degrees, it goes back up. At 0 degrees Celsius, the freezing point, the bond angle is actually greater than this angle right here. So the hydrogens are further apart. Okay, so what that means is when water freezes, the bond angle goes way out, and therefore you can't squeeze as many water molecules into the same space. So let's say that you have put water in a sealed container made of glass, and you put it in the freezer. So as the temperature drops, the bond angle goes down. When it gets to 4 degrees Celsius, the water molecules are as close as they can possibly get. And then when it goes below 4 degrees Celsius, so you go 3 degrees, and then 2 degrees, and then 1 degree, and then 0 degrees, the bond angle starts going up. And at 0 degrees, the bond angle is as far apart as it can get. And so therefore, the water molecules inside that glass bottle begin to move away from each other. So you can't have as many water molecules in that same container. So, of course, what happens to the container? The glass breaks. So you can't put, a bottle of water that's in a glass container in the freezer that's sealed. You'll break that. And, of course, you have to watch that with, you couldn't freeze wine. Wine is like a 12% alcohol. That means it's 88% water. Same thing. You'll break the bottle of wine. Now, if you get to an 80% alcohol, you can put that in a freezer. Vodka, my vodka's in the freezer. It's at least an 80%. It only has 20% water. So I don't have to worry about the bond angles on that. Most of it's, alcohol. So, if I want to make a drink with and I'm not an alcoholic, Anyway, so, that you don't have to worry too much about that. So you want to make a drink with vodka. Vodka's already very cold, You want to make a martini, whatever, put it in, shake it up, a little bit of ice in there, shake it really hard in order to get little shards of ice, and then strain it. Put a little olive juice in it. Got a pretty darn good martini. Very easy to make. Anyway, so that's where my vodka sits. Absolutely. Okay, The other unique thing about water is you'll notice we've got arrows going to the oxygen. Oxygen is an element that is what they call electronegative. And I love this concept. I'll put oxygen is electronegative. There we go. Which means acts as an electron magnet. So let's say I'm hydrogen, and what is your name again? Pardon? Janice? Janet. Okay. That's from Rocky Horror. All right. So this is hydrogen right here. I've got one proton. I've got one electron. That's it. She's oxygen. All right. So when I get close to Janet, who's oxygen, notice what's going to happen to that one electron. It's going to start doing this. It gets off its orbit. It doesn't go completely and stay with Janet. It will come back to hydrogen, but it will go off its orbit. It goes into an elliptical orbit in oxygen. Okay, it goes towards the oxygen, so it acts like an electron magnet. It is electronegative. So electronegative elements are incredibly important. They tend to cause the molecule, because the electrons are being pulled this direction, away from that hydrogen, not off the hydrogen, but in that elliptical orbit. Let's say your proton's right here. The electron goes way towards the oxygen and then comes back. Okay, so you get this elliptical orbit. That means that oxygen tends to carry with it more negative charge because the electron spends a good deal of its time towards Janet or towards oxygen here. All right, so while it's over here, obviously, oxygen is negative and the hydrogen's positive, one proton. But when it comes back, it neutralizes positive with negative, and then it goes back to Janet. This leaves this positive, makes her more negative. So the overall effect of it going into that elliptical orbit is to make oxygen have a partial negative charge. And each hydrogen, because that electron is not doing this. Now, if you just had hydrogen with the electron going around it, so, you know, just hydrogen by itself, you have the one proton and the one electron. Okay, so here's your proton. We don't have any neutrons, and you have the one electron. That electron is going to go around that proton at an equal distance. You got one positive, one negative. It all cancels. There's no charge. But if I have this electron going way over here to the oxygen, well, that's not any longer. It's not a neutral situation. That electron is spending a good deal of its time towards the oxygen. Not that it won't come back, because it doesn't pull it off. It just spends a good deal of its time this direction. So that's what gives the oxygen a slightly negative charge and the hydrogens a slightly positive charge. So if you wanted to draw the structural diagram, and what we're looking at here is an oxygen with a partial, that doesn't look like partial, looks more like that, partial negative charge. Okay, and each hydrogen will have a partial positive. So what we're really working with, one end of the molecule is partially negative and the other end of the molecule is partially positive. This is basically a bar magnet. You've all worked with bar magnets. You got North Pole, South Pole. Well, basically you have negative at one end and you have positive at the other end. That's what makes it a magnet. You have more positives at one end and more negatives at the other end. That's a magnet. Same thing as a battery. What do you have in a battery? One end is positive, one end is negative. It's a battery. Same thing. Okay. water is basically positive, negative. So we do have partial negative, partial positive. So this is actually a polar covalent bond. You have poles. You've got a partially negative pole and a partially positive pole. It is still sharing the electrons, but not equally. Okay. It's an unequal distribution. Like I say, you go into that elliptical orbit, so you do have a polar covalent situation. So, you know, the very cool thing about that is, oh, look at that. That's funny. It's one of the funniest things I've done in a while. All right. So what's really cool about that is if I have a water molecule, say like in a beaker or a glass, and I have another water molecule, so the oxygen's partially positive, and the hydrogens, both of them are partially, the oxygen's partially negative and the hydrogens are partially positive. If I have a second molecule, say like beneath that, the hydrogens again are partially positive, the oxygens are partially negative. It's like two-bar magnets. I get an attraction of the positive end of one water molecule to the negative end, which would be the oxygen end, of the second water molecule. There is a small, very weak attraction. They hold together. They hold together. And that gives the water some very unique properties. So, water has a bond angle, which changes depending on the temperature. Interesting. Secondly, you have the unequal distribution of the electrons. You go into this elliptical orbit with the hydrogen, which makes one end positive and one end a bit more negative, which leads to water to other water, and it sticks to itself, basically. It's cohesive. And then it's also adhesive. If you wash your hands, it doesn't just all fall off your hands, roll off. Some of it stays on your hands. You're going to have to, you know, use a paper towel, whatever, to get that off. You can just air dry it if you want. So that partial positive does have that bond, which is very weak. It's the weakest of the bonds. That one is called a hydrogen bond. Very weak. Yeah, you have the attraction of the positive end of one water molecule to the negative end of a second water molecule. You have to have at least two water molecules, and there is an attraction of one end of one water molecule to the other end of the other water molecule, the hydrogen to the oxygen. But as the hydrogen of first molecule to the oxygen of the second molecule. And that is a very weak bond, very easily broken. Sure, I can take a dropper full of water and pull it out. So I've broken hydrogen bonds to pull it out. They were all attracted to each other. There were a whole bunch of hydrogen bonds in there, but I can take a dropper of water and pull it out. And then I can take that drop and I can just release one drop of water. Well, when that's falling through the air, it hangs together. That whole drop hangs together. Now, it may change shapes a little bit as it falls, but they're held together by those hydrogen bonds. And then when it finally hits the floor, there's enough energy there to break those hydrogen bonds, and then it spreads. Of course, it spreads across the floor very quickly, but you had enough energy to break the hydrogen bonds to do that. So again, you know, water is like one of these really, to me, fascinating molecules, and you'll see it plays a huge role in biology. It is tremendous. Plays a tremendous role. You know, you're anywhere from you're approximately 70 to 94% water. I mean, any living thing is somewhere in that neighborhood. So it's a huge amount of water. Okay, well, let's go back to that, and we'll end with that for today, and we will stop there today.